My name is Yaohui Chen. So one big takeaway I got from today's Security Princess Priscilla's excellent keynote is that we need to approach the security problem from different angles and always take the ecosystem into the consideration, which is one of the inspiration for me when I started this research. So we're going to talk about how we can instantly deploy the hard patches for vulnerable system programs on Android. This is joint work among multiple institutions. So we know that the always belated Android system security update is a daunting challenge for securing the Android ecosystem because every system update requires lengthy tests from different parties, including the chip vendors, Google, OEMs, even carriers. They need to perform the tests, including the security ones, to make sure the update is effective against those disclosed vulnerabilities. Also, they want to make sure the updates will not break any existing functionality. And this has to be done by each of these go-to-market partners along the chain. It is justified practice, but this is in the cost of time. For example, the patch for the CVE 2016-0835, a critical vulnerability in the media server, took almost 6 months to propagate all the way down to the user devices, which is very concerning. So to accelerate this whole update chain, there are multiple approaches being taken currently. First, we have the monthly security maintenance release. Basically, the partners have come to an agreement that, okay, every one of them has to prepare the updates within a month. So this obviously has shortened the overall security update pipeline. Still, the delay to date can still accumulate to several months. So, and secondly, last year Google introduced Project Treble, which took the chip manufacturers out of the equation. However, the updates still need to be tested and done by the OEMs and carriers, so it's not completely effective. Also, there are a tremendous amount of engineering work to be done for this to be effective. And lastly, we have the hard patch solutions. For example, last year in Usenet Security, Karma was proposed to quickly fix the kernel vulnerabilities. And in XL13, Molina et al. Proposed patch trade to quickly fix the user-level applications. And InstaGuard also falls into this category. Its goal is to seal the exploitation windows when those permanent patches are being developed and tested. And compared with these existing works, InstaGuard has two unique advantages. First, it allows much faster hard patch development. And secondly, its patches are what we call carrier-passthrough. To understand these advantages, let's first have some background regarding what kind of hard patches are available in the market. We categorize hard patches into two kinds, the code update-based ones and the policy update-based ones. So for the code update-based hard patches, there are very matured and commercialized solutions in the market. For example, the Microsoft Hotfix and the Ubuntu's Live Patch. These techniques, they are matured. However, they are not carrier pass-through. Why I say that? It's because the partners also have agreement that any form of co-update has to be tested by all of the parties. And it requires unanimous approval from them to reach the end user devices. And so comparing with the code update-based solutions, we found that policy update-based solutions has several advantages. First of all, it's less dangerous, and because it's more restrictive than code. And that is because when you separate the policy from the mechanism, it's much easier to model the whole system's behavior. And in practice, in reality, we also found that it takes much shorter time for the policy update to go through this lengthy update chain. And lastly, we found that there are already existing infrastructure for those policy updates, and it's already well established. For example, Samsung has this SE Android policy distribution platform. It's convenient such that the users just need to download this app from the Google Play Store, and then they can timely receive the SE Android policy updates. So given so many advantages regarding the policy updates, our goal is to utilize this policy-driven approach to quickly mitigate the critical user-level system vulnerabilities. And the key difference of InstaGuard to the traditional hard patches are such that first, it introduces non-code updates. And secondly, its update is restrictive meaning that even the hackers or malicious party somehow get their hands on the updated policies, the best they can do is deny of service. We also call this feature fail-safe. So to use InstaGuard, when we have the bug reports submitted by the third-party researchers to these OEM vendors, they could use our tool to automatically generate the corresponding policies with the input of the bug reports, and the policies could be timely pushed to the user devices, and then InstaGuard can start protecting those vulnerable system services. So the threat model of InstaGuard will adopt this protocol. We trust the kernel and its underlying hardware. And however, we assume the user-level system daemons and libraries, they are benign but vulnerable. We focus on the user-level system daemons because with the security stack of Android today, these daemons are always the attack surface for the attackers to reach kernel. And what we do not handle are those vulnerabilities that are unaware by even the OEMs, also those already compromised system processes. So to realize the goal of InstaGuard, we need to deal with these two unique challenges. First, our policy language has to be expressive to be able to describe different kinds of vulnerabilities. At the same time, it should not be as flexible as code so that it can be restrictive to have this fail-safe feature. And secondly, the policy generation, we want it to be somehow automated so that the vendor-side developers can have an easier life. So the whole system consists of two parts, an online InstaGuard and a RuleMaker running offline to make the policies. Let's first check out the online part, starting with this Android system view. There are several system services, such as media server, and this dashed line eliminates the kernel and user land. And these green rectangles are the components introduced by InstaGuard. So when we have the policies gets updated, which we call the guard rules, our user level service iDaemon will be notified, and it will communicate with our kernel components iDriver to register the policy to the target process's context. And during runtime, before this target process gets scheduled on to run, our iDriver scheduler will populate these policies into the corresponding hardware registers, so that later when relevant events happens, our user level runtime monitor, which we call iMonitor, will be notified and then start taking action. So although this online system is also part of our technical contribution, but for the focus of today's talk, we're going to look more into the policies. So regarding policies, it consists of two parts, a header and a body. The header has these fields, rule ID, target module, and alert decision. And here's are their corresponding fields. The rule ID is obvious, but the target module has the target name and the install binary path. And the alert decisions is the action to add upon when there's alarms goes off. Currently, we support a block, which we terminate the process, or alert, which we do nothing, but just log the events. And the key to describe different kind of vulnerabilities as we lies in the rule body. It's actually fairly simple. It consists of three simple lists of the primitives, breakpoints, watch points, and assertions. And here's are their corresponding fields. The breakpoint allows InstaGuard to pause the execution of the target program right before the vulnerability gets triggered. Watchpoint allows InstaGuard to monitor the accesses to the relevant variables. And assertions allows InstaGuard to precisely describe the data constraints when pertaining to a vulnerability triggering. So you probably also notice there are action fields inside each of the primitives. This is used to chain those primitives together. For example, when the breakpoint gets triggered, its action could be let's activate the watch point. And when the watch point is triggered, its action could be let's check on the assertion. If the assertion fails, its action could be let's act upon the alert decision. This is a very typical way of doing the primitive chaining, but one can go as flexible as needed. In the later slides, I will show you with several real-world examples how we can use this support to describe different kinds of vulnerabilities. So reflect on the guard rule. It's expressive because we can precisely capture the control and data flow of the target program. And currently, we support describing the different kind of common vulnerabilities, ranging from simple ones, logic bug, integer overflow, bug overflow, out-of-bound accesses, and to the complex ones like use out free and risk conditions. And the guard rule is fail-safe, meaning that the buggy, even malicious rule can at best cause denial of service. That is because the InstaGuard online mechanism simply do not support any intrusive operations such as memory writes. So now let's take a look at several real-world examples, how we can use this guard rule to describe different kinds of vulnerabilities. Start with this simple one, logic bug. In this function, UTF-16 to UTF-8 length, this function is used to compute the length of a string when you convert a UTF-16 string to a UTF-8 one. And it has a logic bug in this function, such that in this line 9, the SRC source pointer, it will be mistakenly advanced when this if statement evaluates to false. However, in the else branch, this SRC pointer will be advanced again. The consequence of that is that the computed length of the target string will be shorter than the string actually is. This later will lead to a buffer overrun. So to describe this simple vulnerability, we just need to follow this practice. First, we can place a breakpoint at the vulnerable location, which is line 9. And its action could be activate the assertion, which will describing when this if statement evaluates to false. This is how the real guard rule looks like. It's in XML format. And other than the information I was talking about, there are also rules regarding how to retrieve the real-time value of those relevant variables. For the sake of time, I won't go into detail for this part, but you are encouraged to check out our paper. So now that was just a simple warm-up. Let's check out a more complex example, race condition. And in this race condition vulnerability, there are two functions that could be entered by concurrent thread. If in the second function, you can see that it's trying to access this IO underscore context field of the task start without the attempt to first obtain the lock. However, if at the same time another thread running concurrently executing the first function, and this will free that IO underscore context field. If these two task start pointer happen to be the same, this will lead to a use of the free situation. So to describe this vulnerability, you can follow this practice. This looks a little bit lengthy, but in principle, it's very simple. You just need to wrap those racing entities with the breakpoint, and then with the help of an internally maintained atomic variable, we can simulate the locking operation. And as you can see, with the help of primitive chaining, we're able to describe even the complex vulnerabilities like race condition. And this is how the overly simplified version, I just want to fit this figure into the slide, looks like. So you probably have noticed the guard rule is not very user-friendly, and we do not want that, it's not our intention for the normal developers to use or compose them on their day-to-day life. So that's why we designed guard spec, which is just a high-level vulnerability description. It can hide those low-level details like those primitives from the user developers. And we also build the RuleMaker to automatically synthesize those guard spec into guard rules. Then conversion is based on a rule mapping approach that we wrote the rules based on our empirical experiences. And there are several implementation challenges, such as how to map the source code location into the binary address ranges. You are encouraged to check out the paper, but for the sake of time, I will just show you some examples of the guard spec. So for example, you can see this in the top two guard specs, these are the corresponding ones to those bugs we just saw. And it's much easier to write them. And why I said it's just vulnerability description as opposed to the traditional patch that is describing how to block a vulnerability from being exploited is that, for example, in the buffer overflow, you just need to specify which buffer is being overflown, what is the intended buffer size, and where is the co-location this buffer overflow going to happen. Similarly, for the integer overflow, you describe what's the relevant variables, what is the maximum value, and where is the vulnerable co-location. All these information can be easily extracted from the day-to-day received bug reports. So regarding the evaluation, we tend to answer these three questions. First, can InstaGuard generically block different kinds of vulnerabilities? And how easy it is to use our system? And lastly, what is the overhead, which is the basic requirements. For the expressiveness evaluation, we selected 30 critical vulnerabilities from the Android Security Bulletin from 2016. And those CVE numbers are the one we selected. We wrote guard specs for all of them and successfully convert them into the guard rules. And here's the bug distribution. So in this evaluation, we have several observations. First, most of the guard specs are less than 10 lines. And secondly, for these two logic bugs, they are causing the information leak because of uninitialized variables. We just find that it is very hard to generically block this kind of vulnerabilities without a risk of losing availability. And lastly, we found that in most cases, use after free and risk conditions find their root causes as logic bugs. That is why we have so many logic bugs here. And this finding is consistent with the previous work comma. So regarding the ease of use, we asked the security researchers from Samsung to select from their received bug reports for 4 different types of vulnerabilities, and then wrote the guard spec for each one of them and synthesized them into the rule using our RuleMaker. You can see the average time for them to finish the task is below 30 minutes. That is because the guard spec are just 7 or 8 lines, and also because all this information required for you to compose guard spec can be easily extracted from the bug report, which is just a more detailed version of vulnerability description. So lastly, regarding runtime memory overhead, we further applied those converted guard rules to the binaries and then conducted unit tests on them. And you can see the average memory overhead and runtime slowdown is fairly small. And we finally wrote a wrapper service that contains all of the above vulnerabilities and applied the alternative version of guard rules on this single process. And you can see the accumulated runtime slowdown, which is just a worst case because we are stress testing all those vulnerable paths. And the smaller memory overheads, which is caused by the user space runtime I monitor. And with a larger binary, this overhead is smaller. So lastly, in conclusion, we built InstaGuard to make those hot patches timely available to the users using the policy update approach as opposed to the traditional co-update. And these guard rules we design are expressive yet restrictive so that no malicious party can take advantage of this to abuse this system. And secondly, we built the RuleMaker to automatically synthesize the guard rules. And by having these guard specs, which are just a high-level vulnerability description, this RuleMaker can hide the low-level InstaGuard primitive from users. And eventually, we evaluate our system on those real-world critical system vulnerabilities and review very minor overheads. So with that, I want to thank you for your attention and take questions you might have.
Hi, nice talk. How does your system know when to check the policies? So you create a new policy for a vulnerability in some function, and how does it know now, the phone now know to check the policy for that area? Because you must not be checking policies everywhere to get anywhere near 10% overhead.
So you're asking about the overhead or when to make the policy activate?
Yes.
I mean, which one?
Well, both.
Oh, both? Okay. So let me answer when to activate the policy. So basically, this is related to the online part of the system. So we have a system daemon that is called iMonitor, which acts upon a callback. So when we have policy updates, you will be notified, right? And register this to the, so it's also monitoring the start of the processes. So that, because we also modify kernel, so when the corresponding installed binary path started, we can activate the corresponding policy, even when the process is restarted. And regarding the overhead, so this has to be done with those primitives we're using. So basically, the major overhead comes from the breakpoint, right? So you have a breakpoint, and then you chap, and then you, based on the action field, you go to this, you go to that, and eventually you come back. So basically, this is the, and if the action says we don't take action, and then the process just continues. This is the overhead.
I see. Thank you.
Hi, Mary Ellen Zurko, MIT Lincoln Lab. Fun paper. Do you or will you have a more extensive write-up on the usability testing you did? I glanced at the paragraph in your paper, but I have so many more questions about that.
I did wrote some usability part in the paper, but I did not conduct very extensive research into that yet. So we can continue working on that.
All right, let's thank our speaker one more time.